former citizen. He served back in the late 90s, and then before that he was a grad student in Cambridge, and then he's bumped around places. He has now settled in Gila and Boulder, where he does things related to planet formation and accretion disks as well. So without much else, I will let you take the floor.
Thanks. Great. So yeah, so I'd like to say some stuff about planet formation, and in particular discuss some aspects that are related to disk turbulence and what we might be able to learn about perhaps the early stages of planet formation, especially by looking at turbulence within protoplanetary disks. So this is stuff that's being done by a bunch of people. The disk work, the MHD work I'm going to be describing is being led by Chris Beckwith and Jake Simon, who are both postdocs in Colorado. And then, sort of for fun, I'm also going to show some dynamics calculations, which are being done by Sean Raymond, who used to be in Colorado and is now in Bordeaux, and Nick Mokel, who's a postdoc in Cambridge. So maybe to just sort of set the stage, obviously planet formation in general involves a whole bunch of different physical processes, and some of them are quite messy and unpleasant and difficult certainly to study from first principles. So we think about small particles growing to become larger things within protoplanetary disks on scales maybe less than a millimeter or a centimeter. The dominant physics is really what happens when those particles collide. Do they stick? Do they bounce? Do they fragment? And that's very much connected with the material makeup of those objects. So there are lab experiments to look into that from a material physics aspect. It's not something that's very amenable to first principles calculations. On the other extreme, of course, for a long time, dynamics is an important part of at least the evolution of planetary systems and stages of their formation. As Newtonian n-body dynamics, so that's been studied from first principles for a long time. And then, of course, there's some hydrodynamics, sort of laminar hydrodynamics, things like the accretion of the envelopes of the giant planets, photoevaporation, some interactions between large planets and their disks. So what I'm going to be talking about today is sort of somewhere in between these extremes, aspects of planet formation that have got something to do with turbulence within the disk. And that can sort of come into two flavors. I'm going to be concentrating today on what you might describe as intrinsic turbulence. So this is sort of the same sort of things as we think about in disks in high energy astrophysics environments. So turbulence that is initiated by some kind of instability that is purely present in the gas phase of the disk. Now, of course, there's also other kinds of turbulence. If you have large particle concentration, become comparable to the gas density locally, two fluid instabilities which are quite separate, maybe I'm going to be discussing, which may be very important. And then there's this question of rather disk angular momentum transport. How does turbulence of any kind interact with particles, maybe to concentrate them, and therefore to allow you to grow to larger sizes, and then how the much larger bodies of planets actually migrate. So let me just sort of sketch out where what I'm going to be discussing falls in sort of the bigger picture of planet formation. So let's divide things up in time here. And there's a sort of characteristic timescale which is important in planet formation, which of course is the gas disk lifetime, which is an observationally measured quantity, and that is typically between 1 million years and 10 million years. So that's how long the gas is present. And then we can also divide things up in size, thinking here of particle sizes, so solid bodies, starting all the way from micron-sized objects all the way up to large giant planets, which would be down at the bottom here. And we think we know what the sort of starting point is. Within the disk, we have small particles, which may either be from the interstellar medium or they may have condensed out of the gas, which are sort of micron sizes. This is the initial conditions. And there's a whole bunch of evidence, basically observational evidence, that says in a relatively short time period, some growth of those particles occurs. And it's generally thought that maybe you can grow up to millimeter size scales quite quickly, maybe 10 to the 4, 10 to the 5 years, depending on where you are in the disk. And there's also evidence that even at the end of the disk lifetime, so when the disk has been around for millions of years, you do still have very small particles within the disk, right? You still have micron-sized particles. Not everything has grown up to larger objects. So you're sort of filling in this blue area here. And the physics here is is basically tight coupling, aerodynamic coupling between these small particles and the gas that's present. And maybe there's some kind of collisional equilibrium that's both enabling you to grow to larger sizes while maintaining the small things. Then the next important stage is what we describe as planetesimals, which might be kilometre or 100-kilometre size solid objects. And these are sort of defined as having weak coupling to the gas. So relatively speaking, aerodynamic forces are becoming small on this size scale compared to gravitational forces between the objects. And we think, again, based on some indirect arguments and from evidence in the solar system, that somehow you manage to go from these millimetre-sized particles that are very tightly coupled to these kilometre-sized things that are not tightly coupled, again on quite a short time scale. It doesn't take the entire disk lifetime, it maybe only takes, again, of order of hundreds of thousands of years. And then beyond that, it's the gravity that is the main player, and how that works depends on where you are within the protoplanetary disk. If you're relatively far out, growth can occur quite quickly, up to maybe 5 Earth masses, characteristic scales, and that's large enough to start accreting large gas envelopes, and ultimately you do things like the giant planets in the solar system. And then in the inner part of the planetary system, growth takes rather longer. We think the final assembly of the Earth and the other terrestrial planets maybe took more like 100 million years, and so it finished well after the gas had probably been dissipated. So that's what we think happens. Which bits of this can we observe? Well, of course, we can observe planetary systems, solar system, extrasolar planetary systems. Most of those, with only a very few exceptions, are really quite old systems, billions of years. So there's some potential for dynamical evolution to take place between these sort of primordial planetary systems and what is actually being observed. We see something about these small bodies in debris disks. So these are disks of small dust particles, but the dust is not primordial. It's being produced by collisions from larger objects. That's in this reservoir of planetesimals. So there's an image of one of those debris disks. And then, of course, we see protoplanetary disks off on the left-hand side, primarily in the dust, but also in the gas. So I want to just begin by just showing a few examples of things, dynamical things that we think we sort of understand about this process. So this is an old simulation now of the formation of the terrestrial planets in the solar system. So this is simulator axis and eccentricity on the y-axis there. Jupiter is giant planets, the known giant planets in the solar system are there in their current locations in this simulation. And here we have just a bunch of small objects color-coded by what their assumed initial water content would be. So blue would be water rich, red would be water poor. This is a calculation by Sean Raymond. Let's let that run. So when we let that run, so the time's ticking away on the upper right there, everything's getting stirred up and there's some mixing, and starting in the inner part and then moving outwards, you're having growth through the larger objects by collisions. So this is purely gravity, there's no gas or smaller bodies that might produce dynamical friction or anything like that included in this calculation. And if we let this run, you see that starting with a reasonable abundance of solid material within the disk, you end up with a planetary system that does not look so different from what you see in the solar system. And then we'll just stop this, finish it up. Right? There we go. So it's 130 million years. Here you form 3 terrestrial planets. There's enough mixing that you've brought water into the region where the Earth is, and then there's a few bodies which are still left over which haven't yet been scattered out. So there are problems with these kind of scenarios. One that's discussed most often is the fact that Mars has rather a small mass compared to the other terrestrial planets. It's not obvious why that should be. There's been a lot of work on that recently. But the general picture of forming a handful of Earth-sized planets on pretty low eccentricity, low inclination orbits makes quite a lot of sense. And the same is true actually in extrasolar planets. Much of what we see in extrasolar planets, at least in the regime of giant extrasolar planets, appears to be consistent with a basically dynamical explanation for how the planetary system has evolved early on. So here's one example of that. So this is the eccentricity distribution of extrasolar planets, cumulative distribution, and this black or grey curve with steps is what is observed when you remove those planets that are close enough to the star that they've been affected tightly. And then the green, blue, and red curves are numerical in-body calculations where all we've done is to take 3 planet systems, choose the masses of the giant planets following the observed masses of extrasolar planets, and place them close enough together that they are unstable to gravitational scattering. And what you see, so the different curves here are different because we're thinking about different radii from the star. We have a different influence of physical collisions, so the physical size of the planet matter a little bit. But actually in this sort of test particle, in the point particle limit, which is the green curve, you see you actually agree very nicely with the observed eccentricity distribution. So it may be that much of the sort of strange and unusual things that we see in giant extrasolar planetary systems, are purely a reflection of evolution rather than anything to do with formation. And of course, with other dynamical processes which can take place also at this early time. Now that was a purely n-body calculation. Something we've been trying to do recently is to try and ask, in reality, some of these systems probably scatter or evolve sufficiently early on that gas would still be present. And so observationally, these would be what we describe as transitional disks. And a lot of work with Spitzer on those kind of systems where the gas appears to be going away in at least some parts of the planetary system. So we've been running calculations where we take unstable planetary systems with small amounts of gas still being present, just maybe 5 or 10 Jupiter masses of gas, evolve them and basically look to see whether that small amount of gas nonetheless has important dynamical consequences. Maybe it acts to damp the planetary eccentricities so you don't get something that resembles what is seen observationally. So here's an example of one of those calculations. These are 2-dimensional calculations. Start with 3 planets, just evolve them for some period, and then I think we'll slow this movie down. And so we have 3 planets here, and what we have here is actually the 2 inner ones are going to collide and merge. Now. And then after that, actually, you end up with a stable system. So the system remains basically the same orientation as the gas is either accreted or eventually blown away. Here we're assuming it's being blown away by X-ray driven photo evaporation. So this goes on for a little longer. So this is thinning away as time goes. And orbits remaining fairly fixed. This is then just the final stage of the gas that we dissipated. So there goes. Gas is being sort of blown away from the inside out by the process. Here we end up with a stable 2-planet system in that example. And what we find actually is that those small amounts of gas do not make a large difference to the dynamics. So in particular, if you look at what the final eccentricities of planets are after gravitational scattering, but then also interactions with these residual gas disks, you end up with eccentricity distributions for systems that end up with 1 planet or 2 stable planets that look very much like they would if there was no gas present and it's purely n-body dynamics. So what we find is that actually the most interesting dynamical consequence of having that gas is that you can produce some kinds of systems that do not appear in the purely n-body case. You can produce resonance systems, so you can have a little bit of dissipation before there is any chance for close encounters between the planets. You can push the planetary system into mean motion resonances. And then you can also have circumstances where maybe one of the planets is scattered off the other 2, thrown to large distances, recircularizes and produces an effectively stable triple system. So it's one at least that can last for many billions of years without suffering further gravitational interactions. So there are some questions here which are quite interesting, particularly in relation to some of the Kepler results. Kepler's finding a lot of planetary systems that are quite close to resonant configurations but are not actually in resonant configurations. So how those systems emerge from the gas disk during this transitional phase is quite an open question.
What fraction do you find are resonance?
So we're getting maybe let's say 10% here, but we're only modeling the last 200,000 years of the gas phase. So in these laminar calculations, more or less if we continue longer, we would just get more. And something else which we've been interested in, Sean Raymond's been looking at this a lot, is how that sort of known dynamics, let's say we assume that this giant planet scattering commonly takes place in planetary systems, as suggested perhaps by those extrasolar planet results, how would that impact the terrestrial planets in the same systems? So if we went back and did one of those calculations, such as I've done for the solar system, terrestrial planet formation, but now allow us to have giant planets that are in a less stable configuration, how does that impact things? That's what's shown in this movie. So here we have the terrestrial planet zone again. Here we have 3 giant planets, an exterior disk of small bodies, maybe like the primordial coiled belt. This here is actually the inferred infrared SED of the system. So if we let this one evolve, you see the growth in the terrestrial planet region initially takes place very much like it does in the solar system. But what's going to happen here is that we're going to have an instability among the giant planets that will produce eccentric orbits among the giant planets. And we're going to have a look at what that does both to the remaining material in this outer disk and then to this terrestrial planet region. So we slow this down. There goes the scattering. So we've lost one of the giant planets. We've ended up with two giant planets in this case. And you can see what you actually form here is you form somewhat different looking terrestrial planet systems than what you have in the solar system. So you have in general less terrestrial planets, and those that you have fairly frequently have quite strong dynamical interactions with the giant planets. So they're more coupled to the giant planet dynamics than they are within the solar system. So we've looked at this again with a large ensemble of simulations. You see actually you predict there'll be quite strong correlations between, say, the eccentricity of the giant planets that survive in the system and the number of terrestrial planets that are present in those same systems. Systems that produce things that look like the solar system are those where instabilities among the giant planets are weak or take place at very late times. Okay, so let's go back to this, this diagram of how we think things proceed and what we see. So we see the observed systems, the debris disks, and the primordial protoplanetary disks. Well, the sort of uncertainties here all lie in the middle of the diagram in the places where there are not really any good observations. And I would say, from the big picture, biggest uncertainty is how do these planetesimals form? How do we go from millimeter sizes or centimeter sizes up to kilometer sizes on a short time period? And the question there, some of the questions are basically what is the role of turbulence of different kinds? So there's this intrinsic turbulence that would be present maybe within the gas disk itself. There's also the possibility of these two fluid instabilities that really are only present because you have large abundance of small solid bodies. So streaming instability is an example of that sort of two fluid instability. So what is the relative role of those processes and perhaps others in building planetesimals? Certainly a large uncertainty. Then we'd like to understand turbulence just within the gas phase. Say more about that later. Dynamical evolution I've already touched upon. What we see now can be very different from what is actually formed up 10 or 100 million years after the system begins. And then there are also questions to do with giant planet formation, one of which is when we have these cores, things maybe 5 Earth masses in size, how do those interact with both the gas and also with the planetesimals? Is there a large amount of radial motion of giant planet cores, or do they mostly form in place? And that's still quite an open question in thinking about the formation of giant planets. And then there's also the remaining open question, is there a route to forming giant planets directly through gravitational fragmentation of the gas disk, which might form giant planets or brown dwarfs perhaps at a very early stage, just hundreds of thousands of years after the system was formed. So for the rest of the talk I want to discuss this question of turbulence, and of course this is a well-known problem in accretion disks. Generally, the specific angular momentum in the disk increases outwards, and so if we wish to have accretion onto the star, we need one of two things to take place. We either need to lose angular momentum from the system entirely in the form of a wind, so it might be taking place in some of these protoplanetary disk systems, or we need to redistribute angular momentum within the gas, and turbulence is the normal way that is considered for redistributing angular momentum. Now, in protoplanetary disks, there are a number of possible mechanisms that have been discussed for either losing angular momentum or redistributing it. And I would say the simplest possibility, the simplest model you could consider and try and maybe falsify, is that there are just two of those processes which are dominant or important. So one of them is gravitational instability, which occurs for these relatively low mass disks when the Q parameter starts to approach unity from above. And that's very probably important on large scales within disks and very early on when maybe the disk mass is even comparable to the stellar mass. Okay? So gravitational instability probably can't be ignored, at least in some regions of the disk. And then at later times, when the disk is lower mass, probably stable against gravitational instabilities, And there the hypothesis would be that the magnetorotational instability, the MRI, is the dominant way in which angular momentum is transported. And in ideal MHD, this is very simple. The linear MHD instability that occurs when the angular velocity declines outwards as it does in this. Now we can make some simple models, sort of stepping back a little bit from what the source of the angular momentum transport is, and just ask, well, what are the physical conditions going to be like in different places within the disk, and therefore, how effective would these different instabilities be? So these are some examples of alpha models of disks, where you assume that the angular momentum transport, the viscosity, scales as some parameter alpha times the product of the sound speed squared. So what we're plotting here is radius and accretion rate, assuming a steady state protoplanetary disk. This modeled as a vertically integrated one-zone model. And there are various curves shown here that show which bits of the disk are going to be favorable for different instabilities to operate. So this blue line, which is in the upper right corner, above this to the right, would be where you'd be potentially gravitationally unstable, where the tomb rate Q would be of order unity. So that's typically far out, beyond 10 AU, and at relatively high accretion rates, above maybe 10 to the minus 7 solar masses per year, which is a pretty large accretion rate for an observed Halley star, but maybe small accretion rate compared to what you get early on during the star formation process. Then there's another curve here, this red one, which shows temperature of 800 Kelvin in the midplane of the disk, and this is roughly where alkali metals become ionized. So there's a significant change in the ionization properties of the disk if you are to the left of this line, and therefore you have relatively high temperatures. And that takes place in low accretion rate disks very close to the star, but if you go to younger disks that have much higher accretion rates, you might be out to several AU in that relatively well ionized region. And then this orange curve is also important. That's the radius within which viscous heating dissipation due to the inflow dominates over irradiation of the disk by the star, making some assumption about how the irradiation happens. So what you notice in this is that there's a large region between this red line and this blue line where the disk is neither massive enough to be gravitationally unstable, nor hot enough to be thermally ionized, even to the extent of ionizing the alkali metals. So this is the sort of interesting and problematic region in protoplanetary disks, and there's an argument you can make, which is that in that region, the ionization can be so low that you really have to worry a lot about the non-ideal terms in the MHD equation. You have to worry about the fluid not being coupled to the magnetic field. So as a simple estimate you can do, you define a magnetic Reynolds number as being the vertical thickness of the disk times the alpha end speed divided by the resistivity. Requiring that to be 1 implies an electron fraction that's very small, about 10 to the minus 12, but nonetheless, in this sort of intermediate region, that ionization fraction is quite hard to attain. It's hard to reach even an ionization level of 1 part of 10 to the minus 12. So what is going on in this intermediate region? How is angular momentum transport happening there? So one suggestion is that this leads to a so-called dead zone model, in which the ionization you get in those regions is dominated by non-thermal processes of various kinds, non-thermal ionization. And there are 3 different possibilities. So what you're looking at here is surface density measured from the upper part of the disk downwards, so column density down to the disk, and this is the ionization rate due to various possible sources of ionization within the disk. So one possibility is radioactive decay of some short-lived nuclides. That produces a rather low level of ionization. Another possibility is stellar X-rays, which are certainly present. And then yet another possibility is cosmic rays, which may be present if they're able to penetrate into the disk from the larger scales. What you see is that about 1,000 grams per square centimeter might be a fairly typical surface density in a protoplanetary disk, 1 AU. And that amount of column is more than enough to very efficiently shield both stellar X-rays and even cosmic rays if they were present. So the inner parts of the disk, therefore, will be cold, so they won't be thermally ionized, and they're also well enough shielded by the material above that you don't expect a lot of particles to be penetrating through the midplane and causing ionization for that reason. So, sort of a schematic picture you might draw is one like this, which is based on ideas that Charles Gammy had a long time ago now. Here we have the star with its X-rays. maybe cosmic rays coming into the disk as well. If we're very close to the star, it's hot enough to be well enough ionized that we should be roughly in the ideal MHD limit, so have a sort of turbulent disk in that region. If we're a long way out, then the cosmic rays or the X-rays will penetrate through most of the column, again produce a reasonable degree of ionization. But if we're somewhere in the intermediate region, then the region near the midplane will be cold and shielded, and that will not be turbulent, will not be strongly turbulent at least. So there will be a relative dead zone where there is resistive quenching of the MRI and reduced levels of angular momentum transport.
How far away is that?
So it depends on the accretion rate. This might be a few tenths of an AU, and the downward R might be 10 or 20 AU. It depends on exactly what you assume about the dust properties within the disk. And there's additional complexity, which very much only partly come to terms with, which is that if we look at the induction equation, it's not just this resistive piece which is in principle important. We may also have the Hall effect and ambipolar diffusion being important in different regions of the disk. So here is the plane of density and temperature, and these blue and green curves give estimates of what the midplane temperature and density and the atmosphere temperature and density would be like for a sort of toy model of a photoplanetary disk. And depending on which these regions we are in within the plane, the ordering of the non-ideal terms can be different. So for very small scales, it is the ohmic resistivity which is the most important. But if we go further out, there's a large region where the Hall effect is the largest of the non-ideal terms. And then, of course, if we go to very low density, and the polar diffusion becomes the dominant physics. So in principle, we'd like to understand how each of these terms affects the evolution of the MRI. So that's what we'd like to do. We'd like to simulate these protoplanetary disks, or at least pieces of them, in first principles, obviously in a numerically converged way. That's an important computational aspect, but then also including these relevant non-ideal effects, ideally all of them. And if we could do that, we could then relate that in a sort of further step to the physical ionization fraction, knowing something about the ionization and recombination processes that are present. And from that, what we hope to get is a measurement of the stress, the angular momentum transport within the fluid, but then also how it affects solid bodies of various sizes. So that's what we'd like to do. What can we actually do? Well, that's obviously not as good as what we'd like to do. Very rarely is it? So at the moment, I think I'll show you some results. I think we're making some progress in having simulations of the MRI that are actually numerically converged. So questions of resolution and domain size we can address reasonably well, I think, at least in ideal MHD. For the non-ideal effects, we do a pretty good job with the ohmic diffusion and the polar diffusion. There are some calculations of that, but they're not yet quite the same level as those including the ohmic terms only. And the Hall effect at the moment is not something which we're able to model at anything like the physical strength within protoplanetary disks. So the role that has remains really quite open. And then in terms of relating it to the physical situations within the disk, the ionization sources are reasonably well understood. The X-rays, at least, are measurable quantities in observed disk systems, so that's something we have quite a good handle on. Most of the uncertainty comes instead from the recombination, and because that depends on the size distribution of the dust within the disk, which is a very uncertain quantity. So I'm going to be showing some results from Athena MHD simulations. So using the Athena MHD code, which Jim Stone is the principal developer of that. And so the models I'm going to be showing are stratified in the sense that they have a vertical distribution of density, so they include the vertical component of disk gravity. Most of them are going to be local models, so they're little patches of the disk simulated in shearing sheet type geometry. Also show very briefly some results from global models. What I'm showing today will be just all isothermal calculations with a fixed ionization profile. So we assume that when we consider the non-ideal terms, we assume that the ionization profile is known and it's set by that balance of non-thermal ionization sources against some assumed recombination. For example, just assuming gas phase recombination, which was much better known than the dust recombination rates. And this is our plot here just to show that we can do quite large simulations with Athena quite efficiently. This is the weak scaling efficiency. There's some test problems as a function of the number of cores that are being used. all the way out to the full crating machine. And depending on exactly how it's set up, we can get between about 80 or 90% parallel efficiency even on those very large processing counts. So this is just going to be a little movie showing how this works. Just an ideal MHD. This is a shearing box simulation. So this is radius here, azimuthal direction this way, vertical direction here. Here's the midplane of the disk. So look, first of all, this is the density cut with these simulations. This is the density. So you can see this sort of turbulent flow. See these waves propagating through the disk in the midplane there. And actually here you can also just mostly see the vertical stratification. Here's the magnetic field. Gives a better idea, I think, of how the sort of smallish scale nature of the turbulence within the disk. And I think at the end we just flip back to the disk.
What are these waves?
So these are just density waves that are being stirred up by the turbulence and they're just bouncing around within.
So they angular momentum showing or buoyancy showing?
So they have some role in the angular momentum transport, yes. Okay, so first question you might ask is, well, these are local calculations, which are obviously not representing the full physics within the disk. Are they at least self-consistent in and of themselves? So are they converged with respect to numerical resolution and with respect to the size of the domain that is considered? And some of you know, just not very many years ago, 2 or 3 years ago, there was actually a big debate in the community about whether these local calculations are able to obtain convergence, or is it a case that everything you're getting is just depending on resolution. So here's a plot from Shane's paper of a year ago now. This is showing stress as a function of time for different numerical resolutions. And so you have a red curve and a black curve here at different resolution. And what you can see is a turbulent mess, a lot of fluctuations, but there is no obvious systematic difference here between the numerical resolution. So when we go to these stratified calculations, which are quite different from non-stratified calculations, it appears that they do converge to a well-defined stress as the numerical resolution is increased. And then the lower plot shows a similar thing as a function of the domain size, so taking local patches of the disk, but considering small ones and then much larger ones. This is the x dimension, the radial dimension of the domain, going from quite small domains, just half of the vertical scale height, up to quite large ones, 16 vertical scale heights. The physical resolution is kept fixed, and the aspect ratio of the calculation is also kept fixed. And the squares here show the derived stress. Again, there's no strong trend with the size of the domain. So that's quite good. You can look at other measures of convergence as well. This is the correlation function of the magnetic field in, again, 3 different domain sizes here. Magnetic field decorrelates on quite a small length scale. That's this sort of inner patch here, in a bright red patch. You can see that the size on which that decorrelates remains pretty fixed as you go here from quite a small domain up to a much larger one. So that's sort of all well and good. However, of course, it's also known, actually from a very long time back, from the earliest MRI simulations, that there is also evidence for sort of interesting larger scale fields and perhaps other structures which develop within the turbulence. So here's one example of that, the one that's been longest known. So this is a space-time diagram where what we've done is to take the azimuthal magnetic field and average it over radius and over azimuth. So what you have here is just the z dimension as being the remaining spatial coordinate and time. The colours here are showing magnetic fields of different sizes. So what you see is that we get here a sort of alternating pattern of magnetic fields, where some magnetic field is sort of seemingly forming in the midplane and it's then being ejected vertically out of the domain, being replaced by a field of the opposite sign, and that process is continuing. You can see this is in one of those large spatial domains. It's very uniform in that domain. Basically, set your wristwatch with how this is flipping between one sign and another. This is either 8 or 16 scale heights. Yeah, and so it's surprising because you might think as you go to a very large box it would have many independent pieces, and they would all just make a mess. Okay? And then something that's been discussed more recently is, well, maybe this has an effect also on things that are of more direct importance for planet formation. And one of those would be if you could develop local density maxima within the disk, which would also be pressure maxima, which would tend to concentrate solid particles. So the aerodynamic forces would push solid particles towards pressure maxima, whether they're sort of axisymmetric rings or whether they were more exotic things like vortices. And we do actually see this in these large shearing boxes. So this is a small shearing box, just 2 scale heights across, going up to one here that's 16 scale heights across. These are density fluctuations. In the smallest box, you just see sort of a bit of a mess. But then as you go to larger and larger boxes, you start seeing these coherent structures which actually sort of wander around radially, but have quite long lifetimes, maybe tens, maybe 100 local orbits. And there's a little bit of sort of preliminary evidence when you go to the largest. And so you go from sort of the first box, you see this, to one that's twice as large. The scale of the mode just becomes twice as big, so it seems to be a box-filling kind of thing. There's a little bit of evidence when you go to the very largest box, there's actually significant power, not just on the box scale, but also on twice that. So maybe one is using a physical scale out of it, rather than just seeing something that grows to fill the box. So these are zonal flows, and as I say, they could be important for particle trapping in these pressure maxima. Now, something else we see, which is not a direct interest for planet formation, but I think is quite interesting from the point of view of disks, is when we look at the variability in patches within these flows. So what we've done here is to consider the variability in the disk, in the simulated disk, in fixed sized patches as a function of the domain size. And the different symbols here are showing the total magnetic energy and a measure of the magnetic stress. And the panels here show different places within the disk. This is close to the midplane. This is a little bit above the midplane. So these are parts of the disk that are still quite turbulent. And then this is further up in regions of the disk where the magnetic field is dominant, and so it's not really unstable with the MRI because the magnetic field is too strong. And what you see, so this is a function of the domain size, is that as you go from small domains to larger domains, the variability in the atmosphere of the disk, if you like, remains relatively fixed between the calculations. But in the midplane of the disk, there's quite a noticeable drop in the variability as you go to large domains. I stress these are within fixed size patches, so it's not simply that we're averaging many statistical things together and getting less variability as a result.
How do you reconcile that with that correlation stuff changes?
So you have to squint or turn the lights in. So you look at this, and there is actually this sort of light blue stripe there. Right? So this is related in some way to this fly on this large scale field. Go in the right direction here.
So the figure we have the cycle, how, just looking at one radius, how do things vary with radius?
Which block is this?
This one? No, two. Yeah, that one.
So, so in these calculations, obviously, we just have a fixed omega shearing box, right? So another postdoc, Sean O'Neill, has looked at this a little bit in global calculations, and there, I would say it seems to be at least moderately coherent with radius. So there is some evidence for the same sorts of things, in global calculations where the angular velocity is really a function of radius, and there's sort of scaling as you'd expect.
And you're imposing some flux in this?
So here we're starting with some toroidal flux, but the vertical boundaries are open, so the flux is actually escaping on quite short time. So I would say the sort of the summary of these local results is that although the turbulence in some degree is quite local, we also see these emergence of larger scale magnetic fields which seem to have some actual important consequences. They reduce the variability, at least in the turbulent part of the flow, and they lead to this sort of intermediate scale structure. The density structure would be the thing that would be of most interest from the point of view of particle evolution within disks. Now, this is perhaps related to some features we also see in global simulations. So here's a calculation Chris Beckwith did earlier this year. This is now a quarter of the whole azimuthal domain, reasonably significant radial domain, and also a fairly high vertical domain. So what we've done here to make this more manageable is that we only have high numerical resolution close to the midpoint. So it's de-resolved as you go to larger scales. Now, one of the things we've looked at here is how do local magnetic fields build up within this flow as it evolves. So the calculation we've done, the analysis we've done, is to imagine taking patches of the disk and ask how much vertical magnetic field threads that patch and how much local stress do we have as a result in that fluid element. And that's what's shown in this plot here. So this is a measure of the vertical field strength on the x-axis, and this is the magnetic stress on the y-axis. This is averaged over a large number of grid points and a large number of time dumps. So these red, yellow and blue contours show the distribution of those quantities throughout the simulation. You can see it's a very broad distribution. If I tell you the magnetic field strength, the vertical magnetic field strength, threading a patch of the disk, there are many orders of magnitude dispersion in the accretion stress you see at that point. But if you actually average over this distribution, you get the white curve, and what you see is that as the magnetic field becomes stronger, on average, the vertical magnetic field becomes stronger, on average, the accretion stress goes up. And that's consistent with what you see in local calculations where you impose a vertical field through the domain, where you see that there's a scaling between the stress and the beta of the imposed net field component. And we think this could be interesting because this dashed curve shows the distribution of volume in the simulation that has these values of the magnetic field strength. And you can see this distribution actually peaks, roughly speaking, at the point of the curve where you start to get a turn up due to the vertical field. So if you like, the vertical field, which was not present in these simulations initially, has grown locally to become important enough that it is having some feedback effect on the angular momentum transport within the fluid. Of course, these are short duration calculations. We can't say what would happen if you went on for much longer. Okay, so that was all actually ideal MHD physics. What about the consequences of the non-ideal physics? As I mentioned at the start, you expect there to be less turbulence where either ohmic diffusion or ampolar dissipation is high. That's an analytic expectation that is borne out with simulations. This is work from Jack Simon. This is alpha as a function of magnetic Reynolds number, defined actually slightly differently from how I defined it earlier. If you have sufficiently low magnetic Reynolds numbers, you are quenching the turbulence. And if you plug that and also more recent results on ampolar diffusion into sort of analytic models of protoplanetary disks, you find that these non-ideal effects are expected to have quite a large impact on the accretion rate you can trickle through the disk and get onto the star. This is radius, this is accretion rate. These are some models by zooming by from this year, and the different colours here refer to models where different assumptions have been made about the grain physics. So the black is gas phase only, no grains. Blue is grain scale of 1 micron. The red is grain scale of 1 micron. Small grains which have the most surface area are the things that matter by far the most. And what you see, so a typical observed protoplanetary disk might have an accretion rate of 10 to minus 8 or 10 to minus 9 solar masses per year. You can see that might be consistent with the gas phase result, perhaps in some cases with the result of having 1 micron grains present in the disk. But if you have a large abundance of very small grains, it would be very hard to get even those small amounts of mass going through the disk. So this is saying that dead zones, if you like, are really quite dead if you take at face value the results from these MHD simulations of the ohmic and the ampolar terms. Now, what other consequences might that have? Well, one possible consequence is for giant planet growth. So it's long been assumed that the growth of giant planets initially occurs very rapidly when the core first is able to recruit its envelope in a runaway fashion, but eventually is limited by tidal truncation as the planet interacts with the gas. There's the planet forms a gap, and the gap prevents mass coming onto the planet. So these upper panels here show now the results of two-dimensional hydrodynamic simulations. So these are not turbulent simulations, these are purely laminar calculations, where we've taken an alpha of 0.01 and a thickness of 5%. And these are different planet masses, from a little bit more of a Saturn mass up to 4 Jupiter masses. And in this sort of standard disk, So an alpha of 0.01 is roughly what people who try and estimate alpha from observations of disks typically infer. You need to go to about 1 to 4 Jupiter masses before you start forming a really deep and clean gap, and actually still a lot of matter is flowing across the gap to join the planet. If on the other hand you make a dead zone type disk, where alpha is reduced by 2 orders of magnitude, that disk would also be cooler because there's less viscous dissipation within the disk, then in fact you open up comparably deep gaps at much lower masses, 1 Jupiter mass or below. Of course, this calculation depends on assuming that we can define an equivalent laminar viscosity from those turbulent calculations. Maybe details of the turbulence that really require 3 dimensions and turbulent calculations to look at. Nonetheless, if you take those calculations and estimate what the mass doubling time of the planet would be, as a function here of the planet mass, if you're in one of these standard disks, the mass doubling times are really short. And this is a well-known property. If you take a Saturn mass planet and you put it in just a regular protoplanetary disk, actually it barely opens a gap. And so it can accrete gas into its Hill sphere at a very high rate. So the blue points are from those characters that I was showing you before. These open squares are from our older work by D'Angelo and Lubo. Now, if you instead go to one of these low viscosity disks, you get much higher mass doubling times, and also a steeper dependence, of course, on planet mass. So you get numbers that may be more like 10 to the 5, 10 to the 6 years, which are approaching or exceeding the dissipation time of the protoplanetary disk, getting close maybe even to this lifetime. So I think there's actually some evidence that these longer growth times may actually be favoured by observations in the solar system. So in the solar system, it's actually quite a puzzle why Saturn did not grow to become a more massive planet. And the explanation many years ago was that this was just good or bad luck, that Saturn happened to be forming at a time when the gas in the disk was being dispersed. And that's obviously a possible explanation, but it doesn't fit in very well with what people are now discussing, ideas, for example, where Saturn migrated a large distance in the gas disk, perhaps an interaction with Jupiter that was making that migration. If that were the case, then Saturn would obviously have had to form well before the gas was gone. There's also evidence, more complicated evidence, I would say, from the Galilean satellites. If you look at Callisto, it is not fully differentiated, it's only partially differentiated, and the models for the formation of those satellites generally assume that the gas disk that was present as the Jovian satellites were forming had an extremely low accretion rate. In fact, it would be consistent with the mass doubling time of the planet measured in millions of years. So it would be inconsistent with really gas flooding onto Jupiter during the time when the satellites were forming. So that's for the solar system. Can we say something about this for other disks? And there are some possibilities here. So this is the calculation that Jake Simon's been doing this year, trying to look at the turbulent velocity distribution in MRI active disks. So you can play this movie here. So down at the bottom here, there's like a little movie showing one of these non-ideal calculations, where we have ohmic dissipation in the midplane. So you can see this turbulent layer, again, you have a turbulent layer at the top and the bottom, and you can see there's basically very little activity taking place within the midplane. Now, what we've done is do similar calculations at different fiducial radii. That alters the relative balance of the non-ideal terms. So if you go to large distances, and especially at least if you ignore ampolar diffusion, then as far as the ohmic terms are concerned, you're in relatively ideal MHD conditions. So what's being plotted here is the distribution of turbulent velocity as a function of velocity on a log scale, normalized to the sound speed. So transonic turbulence is obviously the right key. And what you see is that there's a strong height dependence of the predicted velocity distribution. If you're close to the midplane, the turbulence and degree transporting angular momentum has characteristic velocities that are about 1/10 of the sound speed. If you go to the atmosphere above 3 scale heights, then you're having values that are more like sonic speeds of turbulence. So this is seen in basically all of the calculations. Now, if instead you go to much closer to the star, where you have one of these dead zones, then you still see quite large turbulent velocities in the skin of the disk, which is well ionized, but then in the midplane of the disk, you suppress the turbulent velocities by maybe an order of magnitude, so you have much lower velocities in the regions of dead zones. Now, there's a sort of caveat to that, which is that some of these properties have nothing to do with MHD turbulence within disks. They're purely a function of having a vertically stratified disk and exciting turbulence and waves within the disk. So here's an example where we just forced hydrodynamic turbulence into the disk. No magnetic field at all. You still see quite similar vertical dependence of the turbulent velocity. So the feature that is characteristic of having MHD is really seeing this suppression which takes place when you see a dead cell. Vertical dependence is not really seen with MHD processes.
How long do you usually run this for?
So those are run for a couple of hundred orbits. These are also large local simulations. So this is of interest because this may actually be observable. In fact, there's even some claims that this has been observed already. So what you're looking at here are now millimeter observations of molecular lines. This is velocity here, this is flux on the y-axis. The data is this histogram, and then there are some models which have been fitted to this by Hughes and collaborators. And so this has been done for a couple of disks. This is one example, HD 16, etc. It's also been done for TW Hydra, which is a better known protoplanetary disk. And in this case, there's a sort of few sigma detection of velocities that are around 40% of the sound speed in the upper layers of the disk. TW Hydra is instead a limit, which is about 10% of the sound speed. So this would be clearly, roughly speaking, consistent actually with what you expect from the MHD expectation. In the upper parts of the disk, you have velocities that are tens of percent of the sound speed. If you go to mid-plane, we expect somewhat lower velocities. But if you look at that data again, what we're looking at here is the comparison, or the plane detection is the difference between the black curve and the red or blue curve. You can see there's sort of plenty of information in the data, but actually none of the curves is actually a perfect fit to the observed results. So there's still clearly more to be done here. But ALMA is, and these are results from CALMA. A lot of expectation, I think, that ALMA will be able to do a much better job on making this kind of measurement. Okay, so I think I'll stop there. Discuss some progress in these simulations of disk turbulence. I think the limiting factors are physics, especially properties of dust within the disk, which has a very strong impact on how well ionized it is, rather than the purely numerical aspects. The things we've been looking at have been the development of largish scale structures in both magnetic field and maybe the density. This appears to all be connected to the growth of mean fields within the disk, which I think is an important question, how those evolve over longer timescales. And things tend to support this dead zone paradigm, which has quite a lot of consequences for both the growth of giant planets and also for aspects of protoplanetary disks that are observable with ALMA. Thank you.
Question? I have a question. Over perhaps longer timescales, in these dead zones, you're whipping the wind across these things, and that's like atmosphere-ocean interaction, right? You have the atmosphere stirring things. And of course, there's lots of ways of transmitting turbulence in the ocean on somewhat longer timescales. And there's a lot of known mechanisms of transport there, right? If you have any thoughts with respect to essentially just stirring from above.
So I guess in those calculations we've done, the turbulence we do have in the midplane is due to stirring from above, right? It's due to MRI turbulence from above in that case, right? I think that sort of effect would be probably strong if in the infall stage there's a lot of mass falling onto this from above. Whether it would be important later, I think depends on, say if the disk is being photo-evaporated, will actually be, the outflow will be away from the disk, flowing and flowing across the surface, if you like, from that stellar work. But yeah, so I think there's certainly plenty of ways of stirring up small amounts of turbulence within the disk, like it's not going to be absolutely, yes.
For the global simulation you went through, you showed that as the box gets bigger, sort of that variability happens in the subsets as it goes down to the shearing box. I mean, I was wondering if that's somehow some weird artifact of the shearing box. So when you look at the global, or the sort of global disk, have you done the exercise of looking at the variability in that, or is it just not done before? They're similar.
So So I think we sort of looked at it. It's difficult to make the comparison very precise. And the basic problem is that in the global case, you have to remove large-scale gradients before you can analyze anything. And so if you remove the large-scale piece from the shearing box, then actually everything is extremely compact and localized there.
Yeah.
So it's a case of having, I think you need to design an experiment specifically to set up a global calculation where you can make the issue.
Well, how far are we from doing global calculation for subsystem? So what is the side of this and see how many fields generated on the other side of the box?
So for the moment, let's say do factor of 2 or 3 in radius, full 2 pi, and reasonable vertical height. It might be maybe a million hours or that. That would not be large enough to really have a really global coupling. Right, so I think, for sure you would have to do something there. So this perspective, for example, was talked about, so we have to do these calculations in special relativity, so we can limit the velocity to the speed of light. There's not a huge computational cost of doing that. So, in principle, that would be one way just to pretend you're very close to a black hole. Or there are other ways of doing it.
You also want a non-uniform gradient.
In such a calculation, how would you handle an actual amount of stuff?
Yeah, so the calculation I showed was done in pseudo-Newtonian exponentials, not because of any particular interest in black hole accretion, just because that is really mathematical. But there are other ways of doing that. Model down to a possible way of doing it.
Anything else? Anything else at all? Well, let's thank Bill again.